Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be continuing our discussion of the polarization of electromagnetic waves by considering a law that governs polarization intensities. Basically it governs the intensity of light that will be transmitted by a polarizer. And so this law is called Malus's Law, or the Law of Malus. What you need to recall from our previous video, or from our previous videos, or what you need to have already covered before doing this video, is that electromagnetic waves are polarized, and this basically means that the E field has a preferential orientation. You also need to know that we have polarizing filters, Polaroids basically, which absorb light which has polarization along one direction and transmit it when it's polarized along the perpendicular direction. Thus, we might represent a polarizing filter by giving the direction along which it transmits light, or giving the axis whose polarization will be transmitted. So if I have unpolarized light coming in from this direction, let's do it in blue actually, just for contrast, and I have some polarization this way, some this way, some this way, etc., polarization in all directions, then what gets through, assuming that this is an ideal polarizer, is light which is polarized only along this axis. And sometimes the arrow in the polarizer direction just points one way, sometimes it points both ways like so. Either one is understood to be equivalent to the other because the E field is oscillating, and so sometimes it's this way and sometimes it's that way, and we don't really care whether it's this way or that way if the axis is vertical. Okay, so this is unpolarized light on this part. This is a polarizer, and this is now linearly polarized light. So that's what we need to know going into this video. There's another thing that I didn't talk about previously that we do need for Malus's law, and that is that linear polarization is in some sense taken to be a superposition. So what do I mean by that? Let's say that I happen to have light which is linearly polarized, it's traveling in this direction, and the polarization direction happens to be like this. So we happen to be polarized along this axis. All right. Now, let's say that we have a vertical axis like so, and let's say that there is a horizontal axis like so. Okay. That essentially means that we have two components. So if this is like x and y and z, we have two components to the polarization. My polarization direction, which I'm just going to represent as a capital P, should be p sub x plus p sub y as a vector sum. All right, that means that there exists some angle, we'll call it phi, such that p times cosine phi is equal to px, and p times sine of phi is equal to py. Now, I used p to represent polarization, but because we know that polarization direction is really just the direction along which the electric field is oscillating, these statements are just equivalent to saying that for this laser, let's say, for this EM wave, maybe it's a laser, maybe it's an X-ray, whatever, that the E field direction is a combination of E sub x plus E sub y. We know that therefore E sub x is equal to the total E times cosine of phi, and we know that E sub y is equal to E times the sine of that angle phi. So this should be kind of familiar from before when you were doing electric fields and you were trying to resolve electric field directions, let's say. You had to break things up into x and y components. Something similar is going on here. You have x and y components. Now, why does that matter? Well, let's say that we happen to have a polarizer. All right, so I have a polarizer here, and I put the polarizer in some direction. Okay, so the polarizing axis maybe happens to be like this. What is going to get through this polarizer? Well, my transmitted light has to have polarization which is parallel to this transmission axis, like so. But my original light had polarization, oops, I'm not doing a very good job of drawing it, but it had polarization in this direction here. So this direction is neither perpendicular to nor parallel to this axis. If it was entirely parallel to the axis, I'd expect all the light to go through, assuming that there's no loss, that it's sort of an ideal polarizer, etc. And if it was entirely perpendicular to this axis, I would expect no light to go through. Okay. Basically, assuming, of course, that we're not saturating, again, that it's ideal and therefore that it doesn't saturate. Both effects do happen in real life for what it's worth. But as a general rule, if I had, let's say, a polarizer that's oriented like this, and my wave happens to be oriented like this, that is equivalent to, as far as how much wave gets through, that's the same thing as if I had a wave polarized like this and a polarizer oriented like this. Either way, I don't get any light through. And similarly, so no transmission here. Similarly, if I happen to have this orientation and my polarization is also like this, or I have polarization, let's say in a random direction like so, but also my wave is polarized, then in the same direction, then I expect to get 100% transmission. So it doesn't matter whether this is oriented vertically or slashed in some way, as long as the polarization is parallel initially, then all the light will go through. Now, the result is that the light's polarization is unchanged and that the polarization direction will be along whatever this axis is, and up here the result is no light makes it through, or only 0% of the light makes it through, or what have you, no transmission. But this right here doesn't really fit either of these. So this does not fit either case. Neither case. So this is where Malus's law basically comes in. And this is where this whole thing of superposition comes in. So let's say that I happen to have a polarizer like so. Let's say that the polarizer angle or axis is like this. And let's say that my light, which is incident on this polarizer, happens to be polarized along this axis right here. So this is light initial polarization. And this right here represents the transmission axis for the polarizer, of course. And so what will happen? Well, we end up with some angle between the two of them, theta. And one way that we can rectify this is that we can go back to this and say, well, over here I had a polarization direction, and I said I have an EX and I have an EY, and the EX and the EY can add up to this total polarization, and they're related via these cosines of these angles. And I just happen to say like the x-axis and the y-axis are how we would sort of define them in native x and y-axis terms. In other words, if I have a beam that's heading towards you, probably I'm going to have an x-axis that's, left, right, and a y-axis that's up, down. And so if my polarization happens to be this direction, then it has some x component, some horizontal component, and some vertical component. Well, what we're doing here is kind of similar to what we did in Physics 1 when we encountered an inclined plane or a ramp. So we say, let's change the axis so that instead of using horizontal x and vertical y, let's use x to be the axis that is along the polarization direction. So this is new x. Let's draw these in. Let's make them like dark green. This is the new x direction. So this will be my x-axis. And my y-axis just has to be perpendicular to it somehow. So this is my new y-axis. All right, and that means that EX, which happens to also be the transmitted part of the wave, EX is ET, should look like whatever the initial E was times cosine of this angle theta, and EY, which is E absorbed, should look like E times sine of theta. This is absorbed. This is transmitted. Now, where Malus's law comes into play is this. Malus's law, instead of looking at E fields, looks at intensity. Now you'll recall, intensity of an EM wave is the magnitude of the Poynting vector. So we're looking at magnitude of S, Poynting vector. And that magnitude of the Poynting vector, what is the Poynting vector? It is, essentially it's a mu naught, 1 over mu naught times E cross B. But we can adjust from E cross B, magnitude-wise, that should be E times B, and they're perpendicular, so it's just E times B, E field strength times B field strength. But we can replace B with E over C. And so what this means is the intensity I, or if you'd prefer the magnitude of the Poynting vector S, is proportional to the E field strength squared. Now, what does that mean for Malus's law? So here's what Malus Law has to say about this. If I want to look at intensities, let's say that I want to look at I transmitted divided by I incident. Well, that should look like E transmitted divided by E incident, both squared. Okay, where did I get that from? Well, basically, I'm just making use of what I know here, that I is proportional to E squared. This is the same thing as saying that I1 over I2 must be E1 over E2, both squared. Everything else in this equation, in the I equation, is a bunch of fundamental constants that will be the same for I1 and for I2, and so when you do this ratio, those constants will cancel. Okay. This in turn becomes E incident times cosine of the angle theta that's between the two of them squared, divided by, again, E incident squared. So if I cancel my like terms, I end up with a cosine squared of theta term. And so the way that we usually formulate Malus's law is we usually multiply both sides by the incident intensity value. And so what that means is that I transmitted is equal to I incident times the cosine squared of theta, where theta is defined again as this axis between my incident and my transmission axis. And so I have some incident light, it has intensity I incident, it interacts with the polarizer, which is rotated through some angle theta for the transmission axis relative to the incident light, and then the transmitted light is just IT. Now, this all assumes that the light is initially polarized. So we have initially polarized light. What if it's not initially polarized? Well, if it's not initially polarized, then you basically tend to just transmit half of the intensity, because the polarization direction, there is none, and so you have equal amounts of light polarized in all directions. And by symmetry, that means 50% of it will end up being validly polarized along any one direction. And so our equation basically would be something like intensity of the polarized light that's been transmitted by this polarizing filter is half of the intensity of the unpolarized light that was incident on the filter. And that's Malus's law. You can basically add more filters if you prefer. Like you can have 2 or 3 or 5 of these filters in a row with different polarization axes, and you can figure out what is the total polarization as a result of going through all of them, and what's the total intensity is maybe the more important question as a result of going through all of them. And that's it. Now you have polarized light that's polarized along a particular direction, and you can figure out, how much total light is lost. So all that really remains here is to maybe do a quick example or so. All right, so suppose that you have light which is initially not polarized. It's unpolarized light. It goes through a polarizer. We'll take the polarizer's axis to be horizontal. So in other words, if I'm trying to draw this situation out, I have initially light over here. It has no particular direction of polarization, which we can represent by just drawing the arrows in several directions like this. Then I have my first polarizer right here, and the polarization direction is horizontal, like so. So this will represent my horizontal, and actually maybe I will draw it as if we're just looking at it face on. And so this horizontal direction is basically like so. Whoop. Okay, my next polarizer is rotated at 60 degrees elevation from the horizontal. So that means that its polarization direction is now like this. where this is a 60-degree angle. All right, so if I continue drawing my light throughput, this one right here is polarized like this, and this right here is polarized along this axis, 60 degrees. And so my throughput light should have a polarization in this direction, parallel to the transmission axis. Now let's label it. So this right here was stated to be the initial intensity I0. We pass through the first polarizer. It's unpolarized, and we're going from unpolarized to polarized. So that means that I intermediate, or whatever you want to call it, I1, whatever you want to call this intensity, is half of I0. And now we go out the other end. I final should look like I1 or whatever, I middle, I center, I intermediate, whatever you call it, times cosine squared theta, where theta is given as 60 degrees. I final therefore is 1/2 of I0, so that takes care of this term, times the cosine squared of 60 degrees. Okay, and if you put all that into your calculator and you make sure you're in degree mode, this will give you that the final intensity, I final, is 1/8 of the initial intensity, I0, after passing through these two polarizers. Conceptual question: what would happen if we reverse the order of the two polarizers? In other words, what if we were to move polarizer 2 to the location of polarizer 1 like this, and polarizer 1 to the location of polarizer 2 like that? What would happen in this case? Well, we'd actually get the same result intensity-wise as before. Basically, this one would now be the polarizing filter. You'd still subtract half of this intensity. You still have a 60-degree angle. Therefore, you still have a cosine squared of 60. Cosine of 60 is 1/2. Cosine squared is 1/4. So you get an 1/8 overall. Does that mean you have the exact same result as before? No, actually. You have the same intensity as before, but your polarization axis will now be like this rather than the original drawn. Okay? So the intensity is the same as before, but the orientation is different. That's all that I'm going to do in today's video. It's another fairly long one because this is a relatively I don't want to call it a complex topic. I don't think it's that, but it's a complicated to explain and needing lots of pictures and therefore very slow to draw out kind of topic. So hopefully you've borne with me to the end of this video. I know it's kind of on the long end. My introductory one to this set was kind of on the long end as well. My apologies for that. But if you have borne with me all the way to the end, thank you for doing that. Hopefully you found it worthwhile and you learned something from it. And as always, thanks for watching.